Okay, so let's get started again. So in the last class we looked at modeling the K and epsilon equation, and then one phenomena that we used is that there is some kind of a local equilibrium with respect to the production rate and dissipation rate. Okay, so I'm showing here my own DNS data here. So we are essentially looking into the ratio of this production rate to dissipation rate. This production rate here, this means this is actually Pk over epsilon. Capital P here indicates the production rate of turbulence kinetic energy. This is not the model data, this is the exact data coming from DNS calculations. So when I see here, this is of course for plotted for two different types of roughness in a plane coed flow as well as the smooth. So regardless of whether the wall is smooth or rough, you can see that there is a zone where this ratio is nearly 1, right. So the Pk is balancing epsilon, let's say in the middle of the channel here, and this is of course much more dominant when we take only a smooth turbulent plane coed flow, that is this black dotted lines. You can see the ratio is more or less 1 in the core of the channel. So there is some kind of a local zone within your turbulent flow where such a equilibrium exists, okay, between the production rate and the dissipation rate. So you can say turbulence is in some kind of a local equilibrium in that zone, and this concept is what we are using when we model the K and epsilon equation, that the production rate of epsilon, it relied on the production rate of turbulence kinetic energy itself, right. So because of this ratio becoming equal to 1. But if you notice closer to the wall, that's where major activity is occurring. There, this is not true. The production rates are 2-3 times larger than the dissipation rates. So there is no local equilibrium in the zones where there is lot of turbulence generation is occurring and close to the wall. And this is true even when you have there is no roughness also. Even if you look at a smooth wall, you see here the peak generation rate occurs in the so called buffer layer, as I said. That's where you have these peaks located, which is about twice that of epsilon. Okay. So we make use of this concept in modeling, that the flow is locally in equilibrium. The turbulence is in local equilibrium. That means locally in some zone within a flow. This is not true for all types of turbulent flows, but essentially we are using turbulent boundary layers as the starting point for all the modeling considerations, and we make use of this to come to some assumption. Okay. So we made the so called K epsilon model, right. So this is what we did in the last class. So we had two transport equations for the K and epsilon. Okay. So in total now we have, if I take the 3 momentum equations, so I have 3 equations here, and I also have the continuity equation to help me. That gives me one more equation, and to close the Reynolds stresses in the mean momentum equation, we had buoyancy and eddy viscosity, and to get all the terms there, we essentially needed 2 more transport equations, which is our K and epsilon equation. So an expression, any transport equation for K and epsilon. So this gives me 2 more transport equations to solve, right. The eddy viscosity and buoyancy, these are all comes inside the equations here. So essentially you have this many transport equations to solve here, okay. And the only parameters that were not known so far is the 5 model constants. So we had C mu, and then sigma K, sigma epsilon, and then C epsilon 1, C epsilon 2. So if I know 5 of these model constants, then we can go ahead and solve your equation. So we will see how to get these 5 constants here today. Okay. So for that, I'll start with the first one, which is C mu. Okay. To get C mu, this occurs in the eddy viscosity equation, right? So nu T equal to C mu K square by epsilon. So C mu is required in the eddy viscosity, which is of course present in many different terms in the other transport equations. So what I do is, to get this, we use a particular flow problem. Okay. So we consider here, the log law region of a turbulent boundary layer, smooth turbulent boundary layer. Log law region of a smooth turbulent boundary layer. So what is so special about this log law region of a smooth turbulent boundary layer when we look into the budget of the turbulence kinetic energy? So we are essentially modeling the K and epsilon. So if I look at the exact K equation and look at its budget, or even if you look at the 3 normal stresses which are the constituents of the turbulence kinetic energy, right? K is half of ui prime over bar. So that budget I have already shown to you in the previous classes. So if you look into the budget of that, you see that there are 2 dominant terms in the log law region, that is the production rate and the dissipation rate. All others are somewhat smaller compared to these 2. So that's why we have taken this specifically the log law region. Okay, but the model is of course being applied everywhere, even when there is no turbulent boundary layer. You have to remember this. These are model assumptions here. I am taking a very small zone of a particular flow, but the model, the K epsilon model, will be used for all kinds of flows, jets, wakes, combustion, wherever you may not even see a turbulent boundary layer or a log law region. Okay, but these are model assumptions. You have to pay attention here. So if I take a log law region of a smooth turbulent boundary layer, okay, so from the budget, of turbulence kinetic energy, we can see that this Pk and epsilon, that is I just showed you in the previous graph, where Pk by epsilon is more or less 1 in the core, right? So we can see that Pk and epsilon, the production rate of turbulence kinetic energy and the destruction rate of turbulence kinetic energy, are much larger than other terms. Okay, so Pk by epsilon are the dominant terms in the log law region. So we make use of this. So if I have this, then I have the K model equation, right? So if I take the K model equation, so we already have that equation that we derived, which is dou K by dou T plus uj bar dou K by dou xj equal to dou by dou xj. I am just rewriting what has been already done, mu plus nu T by sigma K dou K by dou xj plus your production rate term, which is 2 nu T Sij minus 2/3 K delta Ij times your mean strain rate minus epsilon. So this is your K model equation. So if I take the K model equation here and we apply this log law region where Pk and epsilon are dominant terms, okay. So if I consider that, then what would happen to the entire, as I said, in the entire budget for such a problem, pk and epsilon are the dominant terms. So I would like these two to balance each other. So the equation essentially reduces to, so in the log law region, that is considering turbulence in local equilibrium. Equation 1 reduces to essentially 0 on the left hand side equal to pk minus epsilon to first order. Other terms are smaller. Okay, so that means entire left hand side is 0, the diffusion terms are also smaller. So in such a zone we will have this kind of a consideration. So what do I get for pk minus epsilon equal to 0? That means equation 1 becomes 2 nu t Sij, which is 2 by 2 dou ui bar by dou xj plus dou uj bar by dou xi, alright, minus 2/3 k delta ij multiplied by, okay, I already have this term which is dou ui bar by dou xj minus 2/3 delta k delta ij dou ui bar by dou xj equal to epsilon. So this is the equation as reduced to this simple form in the log law region. So now I'm going to consider the same flow as before, right? We have already seen the data, that is we have used a statistically stationary flow, right? The data has already been shown to such a problem where the flow has come to a statistical stationary state, and then that means this is gone because it is statistically stationary in a fully developed turbulent plane coed flow or a turbulent pipe flow and so on, and it was statistically homogeneous also, right? So statistically homogeneous too, that is you consider the same, consider the fully developed turbulent plane coed flow. Or any smooth turbulent boundary layer, it is going to be the same equation. So that means you had dou by dou x1 of your average quantity here was 0, statistically homogeneous. Statistical homogeneity, and then you had dou by dou x3 is 0, dou by dou t is anyway 0, statistical stationarity. And then when it is fully developed, we also know from data that these two velocity components are 0. This we have already seen and discussed. So I am going to use these considerations in this particular reduced form of the modeled K equation. So if I do all this, so what do I get? Of course, this is gone. So essentially I have now mu t dou ui bar by dou xj, dou ui bar by dou xj plus nu t dou uj bar by dou xi, dou ui bar by dou xj, okay, and then I have minus 2/3 k delta ij. So this particular term exists only when delta ij is 1, okay. When delta ij is 1, what will happen to dou ui bar by dou xj? 0, incompressible flow, right? So this term should go away, incompressible flow, right? delta ij equal to 1 incompressible flow, right. So this term goes away. So I get only this consideration here on the left hand side. So if I now expand these two terms, this is repeated indices. On the right hand side I have a scalar. So both of these two terms has to be scalar. I is repeated twice, j is repeated twice. So I need to expand this Einstein summation that you all know. So I get nu t. This if I expand, I get dou, let us set I equal to 1 now, dou u1 bar by dou x j, dou u1 bar by dou x j. Okay. So u2 I don't even have to look into that part, but anyway I am now expanding first in I, sum of 3 terms here, which is dou u2 bar by dou x j, dou u2 bar by dou x j plus dou u3 bar by dou x j, dou u3 bar by dou x j. I can readily see that this term is gone because u2 bar is 0 in such a flow and u3 bar is 0. Okay, here. So I am considering a very specific flow problem and a local zone there also. So I have only one particular term on the left hand side remaining. So we will see the other term, which is plus nu t. This particular term again I set, let us say I equal to 1 now. So I get dou uj bar by dou x1, dou u1 bar by dou x j. Okay. So now what is dou by dou x1 of any statistical quantity? 0 here, statistical homogeneity. So dou by dou x1 of this is 0, right. Homogeneous, right. This is fully developed here. This is because it is fully developed. So this entire term goes away here. Dou by dou x1 of this is gone. Even if you expand it, you will see that eventually this entire term goes away. The cross term, that is ji ij term, goes away, equal to your epsilon. So now I have this on the left hand side. So if I expand this further, I get nu t times, now I sum in the j direction. So I get dou u1 bar by dou x1 square plus nu t dou u1 bar by dou x2 square plus nu t dou u1 bar by dou x3 square equal to epsilon. Again now statistical homogeneity for dou by dou x1, dou by dou x3, okay, homogeneous along these two directions. Turbulence is in local homogeneity in these two directions. So essentially I get only one term. So colloquially if you write this, this is basically dou u bar by dou y, if y is the wall normal coordinate, right. So I can write this as mu t dou u bar by dou y square equal to epsilon. So your entire equation, the K model equation, reduces to this for a statistically stationary, statistically homogeneous flow along the x direction and the z direction, and considering the log law region of that flow, where only pk and epsilon are dominant terms. If you consider other zones close to the wall, viscous terms are dominant, as I said, then you cannot get rid of the diffusion rates, they become important. So I am considering only the log law region of a statistically stationary, statistically homogeneous in two direction, that kind of a flow, and I get this simplified form of the K model equation. Now nu t knows about C mu, the whole objective is to get C mu here, okay. So what I do now is I would like to multiply both the sides now with mu t. Okay, so I get, so multiply both sides by mu t, I get nu t dou u bar by dou y square equal to nu t times epsilon. Now this nu t dou u bar by dou y, does it ring a bell? Does it remind you of a term that you already know? Sorry? Turbulent shear stress using Boussinesq, right? So the Boussinesq gave us, so if you recall here, the minus ui prime uj prime over bar was your nu t dou ui bar by dou xj particular term. So the minus u1 prime u2 prime over bar is basically this particular term. Okay, from Boussinesq you know that, I can write here. So from Boussinesq, its minus ui prime uj prime is nothing but your 2 nu t sij minus 2/3 k delta ij. This particular term is there. So considering this particular flow, the last term, I mean for a shear stress, let us say I equal to 1, j equal to 2. If I want this particular term, I get minus u1 prime u2 prime. The last term goes away because delta 1 2, right? So that is 0. So I essentially get nu t of dou u1 bar by dou x2 plus dou u2 bar by dou x1. So again here this dou by dou x1 or the u2 term, both are anyway gone. For this particular flow, I essentially get this form here. So this is nothing but minus u prime v prime nu t dou u bar by dou y. Okay, so I am going to substitute that here. The nu t dou u bar by dou y, that particular term is there. So therefore I get here, therefore I get minus u prime v prime term, average of course, whole square is equal to nu t epsilon. But what is nu t? Nu t from the model is c mu k square by epsilon. So c mu k square by epsilon, epsilon, these two cancel out. So I get u prime v prime square is nothing but, or I can write this as basically c mu is now equal to your u prime v prime over bar by k whole square, the ratio. So the whole idea of doing all this now is essentially that in experiments it's much more easier to measure in the logarithmic zone and the quantities that are present there, especially the correlation term. U prime v prime over bar is easier to measure. Turbulence kinetic energy you can get from the 3 normal stresses. So from experimental data we can look at the logarithmic zone, or even from a DNS data we can look and see what is this ratio looks like for many Reynolds numbers. It's not just working for one. So we have taken a flow, no doubt, but at different Reynolds numbers, and also for different flows where turbulent boundary layer is present. So we can do that and look at what this value should be. So if one does this, this ratio essentially comes to, so this ratio essentially becomes c mu from experimental data. If I put this, so this is basically square root of c mu will be u prime v prime by k will be 0.3. from experimental data. Okay, this is experimental data in the log law zone. That 0.3 is a ratio of the turbulent shear stress to turbulence kinetic energy ratio. So obviously with this I get C mu as equal to 0.09. So this is the model constant that you will see in the literature. Okay, C mu value, those who have perhaps used this, you would know that the value is 0.09 for all the K epsilon models, and this is how this value has arrived, one of the constant, and we still have 4 more constants to go. So we have another constant that we will look today,